I start this, let's also say, I don't think I'm going to get to these notes today. Interesting. I just stuff this hat line in the middle. Let's talk about some other things that exponentials model. So what did we close with last time? We talked about radioactive decay a little bit. We modeled that using some exponentials. We solved some equations. What am I going to do today? Let's talk about other things that grow at a rate that is proportional to how big that thing is. And one such thing is populations. Right? If you have a population of rabbits, and this population of rabbits isn't subject to any sort of population control, there's an unlimited amount of food for the rabbits, there are no cars that run over the rabbits, then the more rabbits you have, the faster the population of rabbits will grow. So the population growth grows exponentially, so you can model with exponentials. Another thing is compound interest in a bank. If you have money put in some interest-bearing account in a bank, then the rate at which that money grows is proportional to how much money you have in the bank. So let's talk about that first. Let's talk about compound interest. And let's start with just like the easiest possible warm-up. Let's suppose you put $5 in a bank, in an interest-bearing account. The bank advertises an annual interest rate of 5%. You can actually find those nowadays. And that account also compounds interest at the end of the year. So what does that mean? That means the bank's going to hold that money, the bank's going to do whatever it is that it does with that money. And then in exchange for letting the bank keep your money for a year, it is going to multiply the amount of money you have in the bank account by 105%. The original money you had plus an extra 5%. So, what does that mean? If you each year that passes, the bank multiplies in the amount in the account by 1.05, also known as 100% plus another 5%. Then how much is in that account after 10 years? Well, you have your initial $5. I guess there should be a dollar sign. After 1 year, scales the amount by 1.05. After 2 years, it would multiply the amount in the account by 1.05 again, so 1.05 squared. After 3 years, it would multiply it by 1.05 again, so cubing it. So after the 10 years, the amount of money in this account will be the initial $5 times 1.05 to the 10. Yeah.
You know that doesn't make
Yeah. Yeah, thanks for pointing that out. And if you wanted to know how big that is, well, raising something to the 10th power is basically at the edge of what is like reasonable to do without a machine. So if you want to compute this, let's just see how much is in that account after those 10 years. There we go. Have I typed that all in correctly? Cool. And you expect it to be some long, complicated number because 1.05 to the 10th will wind up with lots of digits. You wind up with about 8.14447. All right, cool. Fair enough? So that's not the only type of interest-bearing account that banks advertise. They also advertise accounts with some annual interest rate, but compounded more than just annually. Right? You'll see some that are compounded quarterly. So what does that mean? And this is the only subtle point figuring out what that means. That means that the bank is going to, suppose instead of having the same $5 in the account with the annual interest rate of 5% compounded quarterly now. So, and 1 quarter is 3 months, also known as 1 quarter of a year. So that means that during every quarter, the bank will act as if you're getting 1/4 of your interest. So it'll act like during that 1/4, you'll get your 5% interest, but only 1/4 of it. So the bank will multiply the money in the account by 1 plus 5% over 4, also known as 1.0125, if you do the arithmetic. That feel pretty okay? All right. And it'll do it 4 times per year, because there are 4 quarters per year. So let's parse out what that means. So after every year, you'll multiply by 1.0125 4 times. That'll give you $5 times 1.0125 raised to the 4th. There's going to be lots of calculator use today, so if you're the type of person who carries a calculator and wants like calculator along with, pull it out. But let's write this down. So in order to avoid myself to do the arithmetic correctly in advance, there's the thing that I'm actually multiplying by. 1 plus 5%, but I'm dividing that 5% by 4. And now I want to raise that to the 4th because that's what it takes to multiply by something 4 times. About $5.25. And I know the dollar is for some reason supposed to go at the beginning of the number instead of the end, but the justification for that was never adequately explained to me, so I'll put it where I put it. We feel good? Yeah.
Is that better to quarterly other than yearly? Because it should be about the same, but is one better? You get more money off of a quarterly?
Let's do the arithmetic to check. So and there's going to be a check for the 10 years in a moment, but let's check it just annually. So if you want to put this $5 in at the 5% interest rate annually compounded, then you would have the $5 times 1.05 just raised to the 4th power. Let's just literally see how it does. 1 plus 0.05. I guess that's the same as 1.05. So it'll give you 5 1/4.
So it's basically the same thing, because you can't have a 4%. Or maybe if it's higher amount, I guess that would matter.
Yeah, so you're probably investing more than $5, so there's not going to be this issue with rounding off to the nearest cent. And the bank shouldn't really round off to the nearest cent anyway, especially if it's tracking compound interest. When you go and close out the account, that's when it gets to do the rounding. But not when it's just tracking the amount of money you have. Then it should be treating it like a floating point number. Alternately, having never seen Superman 3, but having had the plot to Superman 3 explained to me by the movie Office Space, the premise of rounding off to the nearest penny is how the villain in Superman 3 gets rich and challenges Superman to begin with, is my understanding. Because that money still has to go somewhere. So you just round it off to the nearest penny and put it into a separate account that you just keep. But if you're on Office Space, you accidentally round off to not the nearest penny, and then you're in danger of getting caught, so I forget how that movie actually ends. Their workspace eventually burns down, right? Office Space isn't that old a movie yet, is it? It's still relevant. How many people here have seen Office Space? Oh, it's not as many as I was expecting. I've got no cultural cachet. All right, cool. So in order to see something where we'll be able to appreciate the difference, let's see if you left this money in that account for 10 years instead. So then what would the bank do? It's going to multiply by this same quantity. So you have your initial $5, and the bank's going to multiply by 1 plus your 5%, 0.05, divided by 4. And it's going to do that once every quarter. And how many quarters are there in 10 years? 4 times 10 of them? place. So let's see how we do. $8.2181. 8.2181. I guess if I round that off correctly. So now we can actually notice the difference, right? It's a full-blown 7-cent difference in the amount of money that we're getting off of this $5 with the exact same advertised annual interest rate. So that suggests something like if you compound it more times per year with the same annual interest rate, like you're effectively getting more money out of it. And in order to motivate something interesting that's going to happen, yeah, so there's the answer to that question. Quarterly generates slightly more money than annually compounding. But you don't have to stop at quarterly, right? You could put money in an interest-bearing account that yields interest daily, secondly, 1 billion times per year. Let's just see how these performances interact. So, there's a general formula you can get out of this. If you have some initial investment, P, for principal, that you're putting into an interest-bearing account, with annual interest rate R, which is compounded n times per year, and you leave it in the account for T years, then let's explain why this formula says what it says. So just how in the quarterly case, during every quarter, the bank gave you a quarter of your interest. If instead you break it up into n periods per year that it'll compute interest, it'll give you 1/n of your interest during each period, during each individual period. But then it will apply that interest n times per year. So if you wait t years, then n times t periods have gone through. So you get a formula like this for the amount that should be in the account after that time. And now we can straight up compare these numbers. Let's fix the interest rate, fix the initial investment. Let's just let n vary and see what happens. So let's use this formula to do some computations. So I'm going to up to $150 in an account. Annual interest rate is 7.5%, which, right, percent just literally comes from the Latin for per 100. So 7.5% is 7.5 divided by 100 is 0.075. Let's compound it monthly, so 12 times per year. Let's see how much money is in that account at the end of this period. And to do that, let's start by just matching up symbols. What's the principal I'm putting into this account?
150.
150. And I think I'm going to suppress the units. We'll just have to understand that that's in dollars. What's the interest rate? 7.5%. In order to avoid confusing myself, I'm going to write that as 0.075 out of 1 now. How many times is it compounding per year?
12.
How long am I going to hold it in the account?
10 years.
10 years. So, there are all the values. So the amount I have at the end of this period is 150 times 1 plus 0.075 divided by 12 raised to the n times t, so 12 times 10. That look like something that's computable? Via machine? Right. I certainly wouldn't want to have to do this by hand using the techniques that we have right now. And in fact, the calculator is not going to use the techniques that we have right now. the calculator is going to appeal to what's called a Taylor series to approximate this by a polynomial and then evaluate that polynomial. But have I stalled long enough? Has someone just approximated this already?
Like 316.8.
Do I hear a second?
I got 81, but
In fact, give me more digits. 316.81, give me like 3 more digits.
096.
Cool. People feel good? So here's what I'm going to have you take a moment and do. Let's do the same thing, but let's compound it daily, ignoring leap year issues. So with n equals 365, otherwise all the numbers are the same. When n equals 10,000, 100,000, and 1 million times per year. And I think in order to prioritize, let's see, you're going to use a calculator. N equals 365. N equals 10,000. N equals 100,000. N equals 1 million. And once you have your assigned computation done, tell me what you got. Oh gosh, let's see. Is anyone here without any calculator machine today? Okay. That makes this step a little less exciting and absolutely impenetrable. So, maybe with that in mind, I'll do the computation, I guess, for n equals 10,000. So, I'll have my initial investment of 150 times 1 plus 0.075 divided by 1 followed by 4 zeros. I want to wait the same amount of time, 10 years, times 1, 0, 0, 0, 0. And let's just literally, let's use a machine. 150 times 1 plus 0.075 divided by 1, 4 zeros, 1, 2, 3, 4, raised to the parentheses matter 10 times 1, 1, 2, 3, 4. The fact that I got dissimilar behavior suggests to me that I screwed up something about.
Multiply, not the power.
There we go. That now agree with what people got who did it on their own? So, if we go from compounding it 12 times per year to 100,000 times per year, we do a little better. 317.5491. And let's hear everyone else's. Anyone get 365 done? What'd you get?
Got 317.52.
You said 5255?
Yeah.
Cool. So, 316, it's a little bit better to compound daily. It's a little bit better, though, it's starting to get pretty marginal to compound 10,000 times per year. 100,000?
317.5499.
All right, so a little bit better, but you only start to notice in the dime, penny, tenth of a penny, hundredth of a penny place. What if you compound 1 million times per year?
317.54999936.
All right, so I guess up to those 4 digits that we recorded for the previous one, you can't actually tell the difference. So, like, we start noticing something. as you compound more times per year, the amount you get at the end of it keeps getting better. But it like slows down. It starts getting better by less and less the more times you plug it in. So this means that you could talk about like the number you would get if you compounded infinity times per year as just like, what does this quantity become when you replace that million with a billion and then a trillion and then something bigger than a trillion? Just an arbitrarily big choice of big N. What does this quantity seem to get close to? And we see a lot, like it seems to be getting close to 317.55. Well, certainly pretty confident in those digits. In general, this. Okay, so what's the best of a lot of them? There's the one that's the best. They just seem to get close to 317.549. And you know what? Let's just do one last computation to help cement that. Let's take that formula and let's just put like, yeah, there's an asymptote going on. If you want to treat this as a function with n being the independent variable and everything else being held constant, there's a horizontal asymptote. And the word you'll use this when you take calculus next semester is the word limit. There's some sort of limiting behavior as n gets big. And in order to get more ideas about this limiting behavior, I'm going to put like 8 more zeros down. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. It did a little bit better. Not much though, right? And in general, there's a formula you get that is the limit. And this is where Euler's number comes from. If you put an initial interest P into an interest-bearing account with annual interest rate R, which compounds continuously. So you should think of that as being what you'd get if n were infinity. So a horizontal asymptote as n gets big. Then the amount in the account after t years is A of t is equal to P raised to the R, P times E raised to the R times t, where E is Euler's number. So let's run this, yeah.
Okay, can we back up a little bit, because I'm a little confused.
Okay.
So when I got a whole big number with that,
When you did the thing I just plugged into the machine?
yeah.
So I suspect,
But you have an arrow from the n to the t for exponting it that way too. But in the equation, it doesn't have an exponent to the n.
which exponent are we looking at?
The other one, the other equation.
Previous page?
Yeah.
Yeah, okay.
But when you typed it in the calculator, you put an arrow on the 10.
On the 10, there should be some parentheses. So so all of this is in the parentheses because of those. All of those, everything inside of those blue parentheses are in the exponent because of the parentheses.
Yeah, but what digits the times it wouldn't be an arrow for exponent on the 10.
Ooh, so those two are being multiplied. So let's parse out that. So I am going to make that a little bit bigger. And still visible enough? Because now I want to like point to things. So there's the P times 1 plus R divided by N. So far so good? Parentheses. And then what do I need in that exponent? I need N multiplied by T.
That's what I
Oh, and you got something different showing up?
I got a whole big number.
It's because you might have accidentally done an extra zero. I did that and I redid it and it was fine.
Yeah, so like, I was very careful to count the number of zeros that I plugged in. So it could be that the number of zeros you wrote down are different between the two different ones with a bunch of zeros after, is one thing that can screw up that computation. Another thing is, depending on what your calculator is doing, it might be running into like numbers that are bigger than it knows how to deal with, depending on the calculator. Like it could be getting like an overflow issue in like the size of numbers it can deal with, is the other thing that could be happening there. So it could be a calculator number entry, like a user error, or an actual calculator error, like a problem in the calculator. Does that help at all to clear anything up? Okay. So part of the point of this is this Euler formula lets you avoid this issue entirely. Like you don't need to plug in what happens when you plug in n equals 10 billion or whatever, because it's basically n equals infinity. Euler's formula says a of t is equal to p times r raised e raised to the r times t will do the job. Yeah, oh yeah. So let's just check that works out. So let's take a principal p of 150. Let's take the same interest rate as we were using in the previous example, 7.5%. So 0.075. So there's the interest rate R. And let's put the money in the account for those same 10 years. So 150 times Euler's number raised to the interest rate R, 0.075 times 10. And let's see what we wind up with. Hopefully, it's really close to the numbers that we were getting on the previous examples. So, let's do it. And those of you with calculator should calculator along with. And I know this is annoying because I took the formula off the screen. Now it's back on the screen. So let's take 150 times Euler's number E raised to the 0.075 times 10. Type all that in right? Moment of truth. That look pretty close to the numbers we were getting? $317.550002. Cool. And there really is the definition of Euler's number. Euler's number is the thing that you do to make that happen.
Yeah, it's the max amount of money you can make by compounding, okay.
Yeah, so if you have an interest rate that advertises a 7.5% interest rate, you put 150 in, the best possible scenario is continuously compounding. And once n is like 12 even, the difference between compounding annually and compounding 12 times per year and compounding continuously is really marginal. But it is technically the bigger of the lot. Neat. Folks feel pretty okay? All right. So, interest rates are one thing that behave exponentially. But it's not the only thing that behaves exponentially. Anything that grows at a rate that's proportional to how much is in it is an exponential thing. So the next obvious example, like we did radioactive decay, now we've done money in a bank, because the next reasonable thing is population growth. If you have a population that doesn't have anything acting on it to suppress it, you have a population that has access to unlimited food, no predators, then the only thing that holds back that population from growing is how rapidly can parents produce offsprings. And the more parents there are, the more offspring will be generated. So, let's talk about population growth. So there are two models that I'll propose for population growth, and they're both the exact same model. The constants will look different. So here's the first one. So any population can be modeled by an exponential. And that means that if you have any population, then you can model that population as a function of time by initial population times an exponential. I'll use Euler's number for the base because I may as well. Euler's number for the base will be the objectively right choice to make once you start doing calculus, because everything will be harder if you don't. During this class, it'll be more of a marginal case whether this is the best base to use. Times Euler's number raised to the some exponent, raised to the kt for some constant k. So you should think of that k as being like some constant that says something about how rapidly do parents produce offspring. That makes some sense? So there's one model for population growth. Any population can be modeled by initial population times Euler's number raised to a constant times time. The other model is any population can be modeled by initial population times a constant base, which is a parameter in the problem that you don't know, raised to the time. Yeah,
Do you mind just writing those on the board? I have a hard time seeing those.
that's an excellent idea. There are the two models. And there's like a reasonably straightforward connection between these two. That's a true statement, right? Instead of multiplying in the exponent, I could exponentiate twice. So there's the choice of B in the second model. So that's why these two models are the same. Instead of letting this k be an unknown constant, just let each of the k be that unknown constant, and now call it B. So let's use these two models just to complete two problems. Here's the main point of what's left of today. So, let's suppose you have a population of bacteria growing in a petri dish. Does that help? I'm gonna move that way. Okay, good. You have a population of bacteria growing in a petri dish. You start with a sample of 0.2 milligrams of this bacteria. So I guess the initial population is 0.2 milligrams. That feel okay? Let's suppose also that if after waiting for 1 hour and measuring the amount of bacteria, you have 0.3 milligrams. And I am in no way a biologist. I made these numbers up. I did not make any measurements myself. I don't even know if these numbers are reasonable for what you might expect in this situation. Probably not. Anyone here a biologist? Those numbers seem unreasonable, right?
Slightly.
Yeah, right. Right, this bacteria quantity has like tripled in the course of 1 hour. That seems a little bit too fast. And like 1 milligram just of bacteria. Yeah, that's huge. That's too many. But don't care. This is a toy example. If you want to do it with like actual things that you measure, then go measure things first. So if you wait 1 hour, you measure the quantity again, you get 0.3 milligrams. So here's the first thing here's what I'm going to use this information to do. Is there anything in the problem given so far that just tells you what the constant k is? I mean, there isn't anything that tells you directly. We need to figure out that constant k before we can do anything with this model to make a prediction. So let's try to find that constant k. So 0.3 milligrams, that'll be equal to the initial population, 0.1 milligrams, times e to the constant k times 1 hour. People feeling good? How many unknowns are in that equation? Just one? Think we can solve for it? Should we do it together, or should I just wait for you to tell me what k is? We do together? Cool, we do together. So, talk me through it. There's an equation, I would like to solve it for k. What seems like a good first move? I think that's like a good second move, because it's not really an exponential form yet. Because like there's a number multiplied by that e.
Divide by that.
Yeah, so this is an important point. Because of order of operations, e is the only thing that's in the base of that exponent, not the 0.1. The 0.1 is outside of the base. So first let's divide over that 0.1. I do that division correctly? Yeah.
Is it supposed to be 0.2 milligrams, not 0.1?
Yes. And that becomes a 1.5 now, right? 3 divided by 2 is 1.5. All right, now I see an equation that's in exponential form, and all the unknowns are in the exponent, so what should I do? Now say it.
Natural.
Yeah, let's put it in log form with a natural log. So, ln of 1.5 is equal to k times 1 hour, because the amount of time was 1 hour. So ln of 1.5, 1 over 1 hour, is equal to this constant k. Nice. And one of the things I wanted to emphasize in this problem is you notice that I didn't suppress any of the units, which I usually do. This is because I wanted to reveal what units are on that constant k. That constant k says like how many times you multiply e per hour. And in this case, it's ln of 1.5 times per hour. Feel pretty good? All right. So let's use that model to make a prediction. Let's suppose I want to know when will P of t be 1 milligram. So in this case, I want to know when will something happen, so I need to solve something for t. So let's write down the equation that we want to solve for t. So the formula we have is initial population, which is 0.2 milligrams times e raised to the constant k, which I now know, ln of 1.5 times t. And now I am going to suppress the units. I just need to remember that t is being measured in hours. That look like an equation that we can solve again? Yeah, let's start going through the motions. That seems like a good first move. I mean, it's going to be like the same process as the thing we just did, right?
Just divide by the.
Divide by this constant. And let's see, 0.2 is 1/5, so 1 divided by 0.2 is 5. Cool. What next? Oh, well, maybe I'll just gauge. Do people want me to keep talking about this problem? Okay, then I keep talking. What looks like a next good move if you want to get t on its own? So right now, all of the unknowns are inside of the exponent, right? What's like the thing you should do when that's the case?
You do e to the 5th.
Yeah, but you mean log.
Wait.
This right now is something in exponential form?
Yeah.
with the base being e.
Oh, yeah.
So if you want to move it to the other side, you use log base e or ln
Yeah,
to move that to the other side.
yeah, I got that mixed up.
Better to make that mistake in class than on like exams or something. All right, so we basically done. What's left? Yeah,
Divide the ln with 1.5 for the other side.
nice. And I guess this is an applied-ish problem, though. The fact that I started by saying these are all made-up bullshit numbers, they're not even reasonable, means that it feels slightly less applied, right? But let's suppose you actually want to know how long this will take. About how big is that number? I think it's somewhere between 2 and 3.
3.96936.
Cool, like that? All right, so, and let's see if this just like seems consistent. So during the course of 1 hour went from 2 milligrams to 3 milligrams. So multiplied by 1.5. This says that if you wait like about 4 hours, it gets up to 1 milligram. So it grows by a factor of 5 in that time. Neato. That seemed pretty all right. So there's one model. The other model behaves in basically the same manner. The only thing is you have like a different unknown instead of k that you need to find. So let's try to use this other model. So alternately, the population is given by a model that behaves like this. So let's try to do that. So let's suppose you start with a population of 3 rabbits. After 4 days, you have a population of 8 rabbits. Again, like that seems unreasonable. I don't think rabbits reproduce that quickly, even in like the summer seasons. And there's also something fundamentally wrong about this model. Populations don't grow exponentially fast over the long term. Right? There are things like predators that cut down on population. There's only so much food for these rabbits to eat. They're going to start starving eventually. Cars will hit these rabbits. There are constraints on a population as it grows. This model doesn't acknowledge those. If you want something that does acknowledge those, you want something called the logistic model for populations, which we won't hit in this class. Not because it's hard, just because we won't. Let's do it. So, what's the initial population in this model?
3.
3. And I'm going to suppress the units. It means 3 individual rabbits. At time equals 4 days, so I'm suppressing the units on time. You have a population of 8. So, what equation does that give you?
Be 3 times our constant, which is b, which is equal to the 4, that's our time.
Nice. That look like an equation we could solve for b? In fact, does this look like an easier equation to solve for b? Yeah, somehow it does. What do you get for that b? Oh. Should I solve or should you solve? Should I do the walk? Okay, cool. Then let's talk through it together. I would like to solve this equation for b. There's only one instance of the variable b, so read out what the equation, the complicated side says. It says start with b, raise it to the 4th power, then multiply it by 3. So multiplying by 3 is the first thing I need to undo. How do you undo multiplying by 3?
Divide by 3.
Divide by 3. So let's divide that 3 over to the other side. 8 thirds is equal to b raised to the power 4. Okay, what next?
Take the cube root.
I want to take the 4th root.
What?
I want to take the 4th root. Cube root is the
Sorry,
3rd root.
I'm sorry.
You probably meant the right thing, right? Yeah, take the 4th root of both sides. So the 4th root of 8 over 3 is equal to b. And notice, usually you'd be worried about this like plus or minus issue, but that b is the base of an exponent. Are negatives allowed to be bases of exponents? No, so that base has to be positive. So the negative choice is not relevant to this problem. All right, now we know what b is. Let's answer the question that's actually asked. How many rabbits do you expect to have at day 10? So, what do you need to do to address that problem? What is that problem asking you to do? So we figured out the base now. The base is the thing that's written up there that I can't see. That thing underlined in purple, what do we need to do to accomplish that?
Just change the 4 to 10.
Just change the 4
So
to
it's 3 times b raised to 10.
Yeah, awesome. Yeah, and we know what b is now. So 3 times the base, which is the 4th root of 8 over 3, and we need to raise that to the 10th power. And depending on how your calculator formats things, that's something that's annoying to type into a calculator, because you need to take a 4th root and then you need to raise it to the 10th power. But we have tools that make that reasonable. Let's just think about like what that even means. Raising something to the 4th, taking the 4th root is the same as raising something to the 1/4 power. So that's the same thing as 3 multiplied by 8 over 3 raised to the 10 over 4 power. Uh, 10 and 4 have a common factor, so let's cancel that common factor. So that's 3 times 8 thirds raised to the 5 halves, or 2.5 if you like decimals.
34.8.
Does that agree with other people who did the computation? Cool. I see 1 second. Do I see a second? Awesome. So let's look at that. Like on the one hand, like that number got big, but that's just an artifact of exponentials get big quickly. And I guess it makes some sense. In 4 days, the population almost tripled. And now I want to wait like 10 days, it's gonna grow quickly. So I think that number seems sensible. Except it's not a whole number, right? What does it mean to have 34.83 rabbits?
You can't.
Yeah, there's like a weirdness. You're modeling something discrete with something continuous. So there's always something weird here. So really what I think you would want to talk about this model as saying is there will be, let's say about 35 rabbits. And I guess it makes sense that this would be like about because this population of rabbits isn't going to reproduce like clockwork, right? They'll produce a new rabbit when they get around to it. And apparently it's every 4 days, it seems to scale by about a factor of 8 thirds. Cool. That feel pretty good? All right. So, I handed out a new pack of notes. I updated the course webpage to reflect this new schedule. I haven't updated Canvas yet. So the stuff right now that is posted to Canvas allegedly as if it's assigned on days this week are basically all a day behind. And the only one that that's gonna affect deadline-wise is the stuff assigned Friday. Cool. Folks feeling good? All right. Folks planning on having questions for me during out of my office hour today, or maybe at the beginning of class? I don't have an office hour today. At the beginning of class tomorrow? All right. going, but you are allowed to ask me questions about the homework in pausing.